Right. Heat transfer, heat loss from a steam pipe and windy air. So we have this cylinder and it has some temperature and there's wind. So now it's going to cool down because the air is cool. So as always, the first step, calculate Reynolds number. Because this is a pipe, the Reynolds number is not L or X, it is D. So VD over curly V. So the velocity, that's given, 8 meters per second. D, that is the diameter of the pipe. It says that right here, 10 centimeter diameter, which is 0.1 meters. And V, that is from the film temperature of 60 degrees, taking the average of the two. So 1.896 times 10 to the negative 5. Now we can type these into the calculator and get our Reynolds number. 4.219 times 10 to the 4th. That is our Reynolds number. We care about the rate of heat loss, that's Q. So to get Q, we have to get H. And to get H, we get the Newton number. So the Newton number, experimentally for these pipes, is 0.3 plus 0.62 times the Reynolds number to the 1/2 times the Prandtl number to the 1/3 divide by 1 plus 0.4 times the Prandtl number to the 2/3, and then this entire bottom fraction is multiplied to the 1/4 power, and this whole fraction is then multiplied by 1 plus the Reynolds number over 282,000 to the 5/8, and then all this to the power of 4/5. Now this may look like an absolute nightmare because it's just experimental data, and so they had to get a function that matched it as close as possible when doing this. But it's really not that bad because we have the Prandtl number and we have Reynolds number, we just calculated it. So that means we can just substitute those in, plug in the Reynolds number here, and plug in the Prandtl number over here and over here. Be very, very careful with these parentheses though, so you don't accidentally mess anything up. But assuming you don't mess anything up when typing things into your calculator, you get that your Newton number is 124. And the Newton number is defined as HD over K. So we have D, we have K, and we have the experimental approximation for the Newton number. So now we can just solve for H. So K times the Newton number over D is equal to H. K, this 0.02808, and then we multiply by our Newton number, which we said was 124, and then D, which is 0.1. Type all this into your calculator. You get that H is 34.8 watts per meter squared Kelvin. All right. Now for Q. So Q for convection is HA times T S minus T infinity. Before, you might have seen the other way around. Here we just need the absolute value. So whichever one is greater is going first. And because I know that the surface, 110, is greater, that's going first. So we have H. What is A? Well, area is the total surface area of this cylinder that the wind is hitting. So normally the total surface area of a cylinder, you'll have the two ends as well, but we just care about the perimeter. So we know that the perimeter of a circle is 2 pi r or pi d. So this is the perimeter. So now what we can do is we can unroll the circle so that we have our perimeter P along the length. So the total surface area is now just P times L, which is pi d times L. So area pi d L. So we have H, which was 34.8, times the area, so pi times d, 0.1, times L. L is L is 1 because we care per unit length. So 1. So that's pi dl. And then we have to do Ts minus T infinity. So 110 minus 10. That is 1093 watts. There's actually another way to get the Newton number. So you could get it from the experimental approximation, or you can get it from this table. So there's a much simpler formula based upon this table, but this is only for cylindrical pipes. So we first see that this is a circle, a circular pipe. If this was a square, and we would look at the square or a pentagon or something. But we see that this is a circle, so we go to the circle section of the table. Then we look at the Reynolds number. So either way, you do have to calculate the Reynolds number. So the Reynolds number, 4 times 10 to the 4. So we will be in this range at the bottom. Which means the Nusselt number equation we will use is the bottom one. So the Nusselt number is 0.027 times the Reynolds number. The Reynolds number was 4.2 times 10 to the 4. Multiplied to the 0.805 power. Times the Prandtl number, which was 0.7202. To the 1/3 power, which is a significantly easier equation than this thing. We type all of this into our calculator. So this estimate gives 127.9. Again, this is an estimate. Both of these are actually estimates. So 124 versus 127.9, those are pretty close, which means we probably did them both right. Just for the sake of completeness, we can now try and calculate H. So using this Nusselt number instead, we get H is 35.94 watts per meter squared Kelvin. I don't know why I wrote it backwards, but they're multiplied, so it doesn't really matter. And now Q, the area is the same, and the temperature difference is the same. The only thing that's different is H. So we use now this H for Q. So we type all this into our calculator. We get 1129 watts, which is fairly close to our other estimate for the rate of heat transfer. So 2 ways to solve this question for heat loss through a pipe.